This is the video for section 11.6 on absolute convergence, the ratio test, and the root test. So as the title suggests, there are three concepts to deal with. The first of these is absolute convergence. So definition says that a series of terms an converges absolutely, or is absolutely convergent, if the series of absolute values converges. And the point of looking at this, there are lots of points, but the main one is in the following fact, that if you have a series that converges absolutely, then that series also converges. And this may look like a strange thing, right? It says that the series of absolute values, if you look at that and that converges, then the original series converges as well. But the point is that sometimes absolute convergence is easier. So let me show you an example of that. I claim that the series n equals 1 to infinity of sine of n squared plus 1 over n cubed converges. And the way that I'll show that is by showing that it actually converges absolutely. So I need to show that the summation n equals 1 to infinity of sine of n squared plus 1 over n cubed in absolute value, I need to show that that series converges. And the way that I do that is by using the comparison test. And what am I going to compare it to? Well, the point is that I always have the absolute value of sine of anything, in particular sine of n squared plus 1, in absolute value is less than or equal to 1. And of course it's always non-negative. So when I divide by n cubed, I know that that's less than or equal to 1 over n cubed. And this is the same thing as the absolute value of sine of n squared plus 1 over n cubed. I know that that's less than or equal to 1 over n cubed, and it's also greater than or equal to 0. And since I know that the series with these terms, so this is the summation n equals 1 to infinity 1 over n cubed, that converges because it's a p series with p equals 3, which is greater than 1, and so the comparison test says that the summation over n of absolute value of sine of n squared plus 1 over n cubed also converges. And so because of the fact, I get to conclude immediately that the original series that I started with is absolutely convergent, so it's convergent. Okay? So the idea with this is that sometimes it's easier to check that a series converges absolutely than it is to check that it converges. For other examples like this in the text, you should see examples 1 through 3 in the text, and one of those comes with a warning that if, let me say it this way, some series can converge but not converge absolutely. So the test from the previous page that says that if you have a series that converges absolutely, it converges, you can't reverse that process. Okay? And that's discussed in example number 2 in the text. Example number 2. And for this reason we have another term that's what it means for a series to be conditionally convergent, or it converges conditionally. And that happens if it converges, but it does not converge absolutely. Good. Now, the next topic in the section is one of 2 tests for absolute convergence, and that's the ratio test. So, for the ratio test you look at the following. So you want to look at L, which is my letter for the limit, as n goes to infinity of the following ratio. So we take the absolute value of the n plus first term of the series divided by the nth term of the series. And the ratio test has 3 pieces to it. So the first piece says that if L is less than 1, then the series with terms an converges absolutely. In particular, because of the fact on the previous page, it says that the series converges. On the other hand, if that limit is strictly greater than 1, then the series that we're looking at actually diverges. So if that limit of absolute value of ratio is less than 1, then it converges, and if that limit is greater than 1, then it diverges. In the middle case, if L equals 1, and here you have to be very, very careful, in that case, the ratio test is inconclusive. So this is like the situation that we saw previously when the test for divergence is inconclusive. It means that you have to try something else. Okay? And I want to make a special note here, and that is that the ratio test is good for some tests and not for others, but it is mostly good for series with exponential expressions so that is with things of the form r to the n and series with factorials. So things like n factorial. factorial. So we'll see how this works in the next example. So I want us to consider the series, the summation n equals 0 to infinity of negative 3 to the n over 2n plus 1 factorial. And I'm going to rewrite this because when I take the absolute values, the point is it gets rid of the signs, and that makes life a lot easier. So we'll rewrite this as the summation n equals 0 to infinity of negative 1 to the n times 3 to the n over 2n plus 1 factorial. So when I take this bit here inside the summation is going to be my an. Excuse me. So when I take the absolute value of that, what that does is it gets rid of the minus sign. So it gets rid of that messy negative 1 to the n that we have up there in the numerator. And we're just left with 3 to the n over 2n plus 1 factorial. And similarly, when I take the absolute value of an plus 1, right, that's the other piece that I need inside the L that defines my ratio test, and I'll rewrite that in a second. This is 3 to the n plus 1, right? So my subscript n plus 1, that's the thing I put in the exponent here because my an had an exponent of n. And on the bottom we do 2 times n plus 1 whole thing factorial. Again, because my subscript n plus 1 is what goes in for n. And when I simplify this bit here, we get 3 to the n plus 1 on the top, and I get 2n plus 3 factorial in the denominator, and that's just me multiplying out that 2 times n plus 1 plus 1. Now the limit that I need to take for my ratio test is the limit as n goes to infinity of the absolute value of an plus 1 over an. It is absolutely crucial that you get the n plus 1 in the top and the n in the denominator. So when I put in these two pieces that I collected up on in the previous line, that's the limit as n goes to infinity of 3 to the n plus 1 over 2n plus 3 factorial in the top, and 3 to the n over 2n plus 1 factorial in the denominator. Now I'm going to do a little bit of algebra. That fraction in the denominator, I'll flip it upstairs. So we end up with 3 to the n plus 1 over 2n plus 3 factorial times 2n plus 1 factorial over 3 to the n. And the point with this is that we're going to get some interesting and useful cancellation that comes from it. The first cancellation is easy. This 3 to the n cancels all but one of the powers of 3 from the numerator. And in order to figure out what the other cancellation is, I'm going to rewrite those factorials as follows. So I have the 3 that I had before, and now my 2n plus 1 factorial says multiply by all the powers going down. So 2n minus 1, dot, 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 down to 2 times 1. And in the denominator I have 2n plus 3 2n plus 2, 2n plus 1, 2n, 2n minus 1, down to 2 times 1. And the reason for writing out all those terms in the denominator is so that you can see exactly where the cancellation starts. I have a factor of 2n plus 1 here that cancels with a 2n plus 1 there. I have a factor of 2n here and a factor of 2n here. 2n minus 1, 2n minus 1. All the terms, all those factors cancel, and I'm just left with these bits here. So what that simplifies to is, as my L is the limit as n goes to infinity of 3 over 2n plus 3 times 2n plus 2, and that, because I have no powers of n on the top and I have n squareds in the denominator, is going to equal 0. Now, because that limit is less than 1, my ratio test, if you look back at it, that tells me that the series that I started with converges absolutely. So in particular, it converges. And you can see some other examples like this in the text, specifically examples number 4 and 5. The third topic we have in this section is the so-called root test, which is another test for absolute convergence. In this test, instead of using the limit of the ratio of the absolute values, we use the limit as n goes to infinity of the nth root of the absolute value of the nth term. So we only use one term, but we take its nth root. And when you compute this limit, assuming that you can actually compute it, the test is exactly the same as with the ratio test. So if L is less than 1, then this series of terms an converges absolutely. In particular, it converges if that limit L is greater than 1, then this series diverges, and 3, if L equals 1, then this series, then this test is inconclusive. Right. So exactly the same format as we had with the ratio test. So let's see if we can fit an example below this. So I want us to look at the summation n equals 1 to infinity of the following expression, minus 2n over n plus 1 raised to the 5n. And I'm going to rewrite this twice. So first of all, we're going to pull out that minus sign. So I get a fraction with minus 1 to the 5n times 2n to the 5n all over n plus 1 to the 5n. And the other way that we'll simplify that is by rewriting all that stuff as a nth power. So this is the summation n equals 1 to infinity of negative 1 to the 5n times the fraction, so 2 levels of parentheses here, 2n over n plus 1 to the 5, all raised to the nth power. And those are basic properties of exponential expressions. So the point here, again, this entire thing is my an. So when I take the absolute value, the signs disappear, and absolute value of an is just going to be 2n over n plus 1 to the 5 quantity to the n. And so the L that I'm interested in for my root test, so it's the limit as n goes to infinity of the nth root of that entire expression. And here's the key point. The key point is that this n gets canceled out by the nth root because I have positive things inside the root. And so we end up with L equaling the limit as n goes to infinity of 2n over n plus 1 to the 5. And this is much simpler to compute. The limit of 2n over n plus 1 is just 2, and so we get 2 to the 5 power. And now that tells us that our L is strictly greater than 1, right? 2 to the 5 is larger than 1, so our conclusion is, by the root test, we conclude that the summation n equals 1 to infinity of minus 2n over n plus 1 to the 5n, that series diverges. And the thing to note about this one is that the root test is good for series with exponential expressions. So things of the form r to the n. Just like we saw in the example here, I have that entire expression raised to some nth power, right? That was easier to see when we simplified it. And the key idea is that when you take the nth root of an nth power, that nth power disappears. Okay. So you can see another example like this in the text, which is example number 6. And this is the end of the lecture on section 11.6.